Okay, thank you very much for the introduction, and thank you to the organizers for this great conference. I'm really happy to be part of it and to be able to present my work here. So yes, I will be talking about resolved stellar populations in galaxies, and I will be showing. But first of all, sorry, I forgot. So yeah, I'm Justus Neumann. I forgot to present myself. I'm a postdoc at the ICG, University of Portsmouth in the UK. I will talk about stellar populations in galaxies, and I will touch a bit both of the extremes. I will present two different projects. On the one hand side, I will make use of a huge data set. Using the Manga Galaxy Survey, I will take about 10,000 galaxies and look at globally, from a global perspective, what drives stellar metallicity in galaxies. And then on the other hand side, in the second project, I want to present to you like what can we study when we go really into really high detailed, high spatial resolution study. In this case of the bar components of galaxies, and what can we learn about the stellar populations there. So first of all, about the Manga study. So about stellar metallicities in galaxies. So we have heard already in this conference as well, there's a well-known established correlation, a global relation between mass and metallicity of galaxies. So the higher the mass of a galaxy, the higher the metallicity. And while we usually believe this is due to the fact that higher mass galaxies, due to the gravitation, have larger potential wells and are more able to retain the metallicities and successfully recycle them into new population of stars or generations of stars. And with the advent of IFU surveys, we can go now and look if this holds true, if there's a relation that corresponds to this locally. So a relation between the metallicity and the local stellar surface mass density in galaxies. So there have been a few studies about them. Many of them actually focusing on gas phase metallicity, not so many on stellar metallicity. And then there's, of course, a lot of studies about metallicity gradients in galaxies, so radial metallicity gradients, both gas phase and stellar metallicity, again, which have been found mainly to be negative. But some more recent works have shown that actually when we go to lower masses, and they can be quite flat or even reverse and be positive. So with the huge Manga sample, I want to go and study this in detail, and how is stellar metallicity locally connected to the stellar surface mass density and the galactocentric distance in the global mass morphology plane. So the sample is drawn from Manga. This Manga product lunch, the internal product lunch 10. So this is about 8,000 galaxies that we selected for this study. And these 8,000 galaxies have about 3 million spectra from Voronoi bins. And each of these spectra we fit with our Firefly code. And actually the catalog that we produce with this, I show a post about this in session 1 of this conference. So we have a lot of data about the resolved stellar populations, and now we can take all this data and first of all, see if we can confirm and find the same global mass metallicity relation for the Manga galaxies. So I plot here, first of all, so each point in these diagrams are single galaxies. So I plot the central 3-axis against age and metallicity against the total stellar mass of the galaxy. And on the left-hand side, we see for the age-mass relation that there's a slight trend with older ages towards higher mass galaxies, but not very steep. And we separated this into early and late type galaxies. So kind of the approach to separate passive and star-forming galaxies. And we see that early type galaxies, of course, at a fixed stellar mass have older ages. But then, of course, more interestingly, on the right-hand side, we see this strong correlation between the metallicity and the total mass of the galaxy. And in addition to this, we see also that early type galaxies at a fixed stellar mass have higher metallicity than late type galaxies. So this is in agreement with some other studies, for example, also this study by James Truslove, who also presented at this conference. And now we can look not plot single galaxies, but really single spatial elements in these galaxies and show the spatially resolved counterpart to the study, which is metallicity against surface mass density. This is a density plot of about 3 million spatial bins. And we clearly see, so the contours show the densities here, we clearly see that there is a correlation. In white, I show here the median of this correlation, and then I also fit a linear trend to this. So we can learn from this just generally like plotting all the galaxies and all radii and everything just into one diagram. We can see there is a correlation, and surface mass density really drives metallicity. But the question is this the only driver, and can this explain all the variations in metallicity? And so where does the scatter and this relation come from? So we want to look a bit deeper into this. And now in the next plot, I show you again the same metallicity against surface mass density. And now I color code here the radial distance of each of the spatial bins to the galaxy center. And then in addition to this, I also want to look of how does this relation look like for galaxies of different total stellar mass. So this is what the contours show. The contours here from light gray to dark gray show increasing total stellar mass of the galaxies that contributed to this plot here. And we see when we move along from the lowest mass contour to the highest mass contour, so from light to dark, we see that we have higher metallicities for higher total stellar masses, as we learn from the global mass metallicity relation. But we see that we kind of move along this this metallicity surface mass density relation. So the scatter isn't really explained by the total stellar mass, but rather by the radius. So if we look at the radial distance, there we see a trend that is almost like perpendicular to this relation. So the scatter seems to stem from the radial distance actually. So let's plot things against the radius. First of all, metallicity gradients. Again, so there are many studies about this. Now we can use all the data that we have here to plot metallicity gradients. So each of the panels shows metallicity against radius. And I separated here from left to right different total stellar masses. So left, the lowest mass bin, and the rightmost is the highest mass bin. And then on the top, we have elliptical galaxies, then S0 galaxies, and on the bottom, we have late type galaxies. So you show I showed density plots again of individual spatial bins, and then I show in black the median and orange and linear fit to the inner one effective radius. And we clearly see that in most of these panels, the metallicity gradients are negative. But if we move from the rightmost towards the left, so to lower masses, we see that gradients become a bit more flatter, and especially for in the bottom for spiral galaxies, we see that for the lowest masses, they become flat and even then reversed, and we see a positive trend for the lowest mass spiral galaxies. So we know that surface mass density gradients are always negative, so there must be, so surface mass density drives metallicity, but there must be something additional driver. So to strengthen this point a little bit, I want to show you the last plot for this part of the talk, which shows the surface mass density against the radius. And now I color code by the mean stellar metallicity. And here I want you to, so these are again the same mass bins from left to right and morphologies from top to bottom. What I want to show you here mainly, so there's a lot of information, of course, but when you look at, for example, the middle mass bin in the middle, and then on the top, just for example, and you look at the fixed surface mass density, so fixed on the y-axis, then you see when you go from the innermost region of a galaxy out towards larger radii, you see that the metallicity actually increases with radius. And this is true when you look at other panels. This is true in most parts. So sometimes you have when you look at the same color, you have like horizontal lines. So metallicity is not changing much at fixed surface mass density. But in many cases, you have an increasing metallicity at fixed surface mass density. So this means that there must be an additional radial-dependent driver of stellar metallicity. And cosmological simulations have shown that there are possibilities. So there are like inflows, outflows, radial migration, or inside-out quenching. So all these things can distribute metallicity radially. And we still need to explore this further in order to understand how this influences exactly the metallicity distribution in galaxies. Now, for the second part, now I want to go to stellar population in galaxy bars. So this is from a different survey, different data, and now looking really at high spatial resolution and just a very few 9 objects. What can we learn from the stellar populations? So there are fossil records, so we can learn about the evolution, of course, now in this case of bars, about the formation of the bar or dynamics of stars, radial mixing, stellar migration, trapping of the stars by the bar, and star formation quenching in the bar and surrounding disk. By doing this study, we also built a very excellent extragalactic reference data set for studies of the Milky Way bulge or bar. Again, we use full spectral fitting with different code in this case. And the data is from the timer survey. So there is a pre-recorded talk by Dimitri Gardotti about the survey in session 2. This is a survey of 24 very nearby barred galaxies with Muse data. And I selected 9 galaxies for my study here. So these are the 9 galaxies. These are Spitzer images. And in black, you see the outline of the Muse field of view. So you will see in the following 2-dimensional stellar population maps of the Muse field of view. So you can see really that we go really into the center of this galaxy, looking in detail of what is happening in the bar. Well, first of all, when I plot ages, so these are our light-weighted quantities. When I plot ages, you see there are, so in yellow, we have old ages. You see that these bars, which are shown here as black ellipses, they're mainly older than the surroundings. Then we can look at metallicity. Now, high metallicity is yellow. So again, we see a lot of yellow inside these black ellipses, and we see that actually bars are more metal-rich than the surroundings. And then we can also look at magnesium over iron. And now we see actually that there's that the stellar bars, so inside these black ellipses, we see a little bit lower magnesium over iron, so they're less enhanced than the surroundings. So these are all just more general trends, so without looking in detail in some of these bars, but the trends were quite clear. So we have that bars are generally older, more metal-rich, and less alpha over iron enhanced than the immediate surroundings. So I'm not talking about the outer parts of the galaxies, but really the central parts. And now we can, instead of showing just the mean values, we can go a step further and now look at the full star formation history. And to do this, we can't show 2D maps, so we have to make 1D cuts, and we do this the following way. When you look at the top right here, you see the main stellar orbits in a bar potential. So the bar is here horizontally, and you have these elongated orbits along the bar major axis. And what we do here is doing cuts perpendicular to these orbits, because this will give us the possibility to best kind of try to separate the different stellar orbits in the bar. And then on the left-hand side, I plot the star formation history of one of the cuts for one of these galaxies. So this is the cut number 2, as I show on the bottom here. So at r equals 0, we are on the bar major axis. then the two white lines, vertical white lines, show the width of the bar. So we're going across the width of the bar. And then on the y-axis, you see the age, and then the color is the mass fraction per gigayear. So this is showing the star formation history. And first of all, you can clearly see on the bottom left and right that there's a lot of recent star formation outside of the bar in the disk. So this is not interesting right now. What I want you to look at is the V shape that is clearly seen in the intermediate to old stellar populations there. And this is showing us that there are more intermediate age stars close to the bar major axis. And then the old stars are across the whole bar. So this, looking back at on the right-hand side to the stellar orbits, this shows us that younger stars are on more elongated orbits, very close to the bar major axis, whereas older stars are more rounder orbits.
1 minute left.
Okay, thank you. So second to last slide. So we compared this very interesting result to MHD cosmological zoom-in simulations, the Auriga simulations. And I want to show you for one galaxy of these simulations, the example that we find something very, very similar. So on the top, you see there an age map for one of the bars. You can see the contours, which clearly show the bar here horizontally. And then you can see that clearly younger ages are close to the bar major axis again. And then if you go towards top and the bottom of this map, you see older ages towards the outer parts of the bar, like from the width of the bar. And in the simulations, you can easily take stars of different ages and then plot the stellar mass densities, which is shown on the bottom. And then this more easily visualizes that the young stars form this thin part of the bar on the bottom left. And if you take the older stars, then you get this rounder part of the bar on the bottom right. And this has been seen before in n-body simulations as well, something similar. This was called kinematic fractionation. And but yeah, this is the first time this is seen in cosmological simulations and in these Muse observations with spectacular great spatial resolution. And so I come to the summary slide. So there were two different projects. In the first project, we had the very large sample where we could look at drivers of stellar metallicity in galaxies, and we found that stellar metallicity is driven locally by surface mass density. But at fixed surface mass density, the metallicity is constant or increasing with radius, which calls for an additional driver of stellar metallicity that kind of flattens gradients or can even reverse them. In addition, this was the main point there. And then for the stellar populations in bars, we have seen from the Muse observations and in the zoom-in simulations that younger stars in bars are trapped on more elongated orbits, forming a thinner part of the bar, and older stars forming a thicker and rounder component of the bar. In addition, we found that bars are in general older, more metal-rich, and less alpha enhanced than the surrounding disks. And yeah, thank you very much, and I'm happy to take any questions.